This is SP-103 visualizing black box models with SHAP and Line, and I am Dane-Tran. So this is our project overview. What is the project about? We built a full machine learning pipeline that makes AI decisions explainable. Training an XGBoost model on the UCI adult income dataset to predict whether or less a person makes over or under 50K a year. From these predictions, we applied SHAP and Line to open up the black box model and explain every prediction. And why does this matter? This matters because most machine learning models are black boxes, or in other words, you don't know why it comes to the decision that it has made. And so their decisions and the kind of thought process is unclear. And then with tools like SHAP and Lime, this helps us understand why this decision was made, which features drove it to make that prediction. So more on what a black box model is. A black box model is any machine learning algorithm where the internal logic is too complex for humans to interpret directly. We provide inputs and receive outputs, but the reasoning in between is opaque. Example includes a neural network and ensemble models like random forest and XGBoost. They're powerful but difficult to interpret without explainability tools. And then why did we choose XGBoost? We chose it over other algorithms like random forest, a neural network, or logistic regression because it has high accuracy on tabular data and native SHAP tree explainer support, and also is faster at training. So this is kind of the project plan we went about. We started with data, getting our data set and pre-processing it, which includes loading the data set, handling missing values, and then encoding categorical values such as educational levels and such. Then we started training our model, the XGBoost model. We fine-tuned our parameters, and then it started producing predictions. And then we implemented the SHAP and Lime explainability features. We use SHAP for global explanations, as well as it also gives local explanations. We use Lime specifically for just local explanations. And then both of these help us analyze feature importance. And then from there, we analyze our results, such as the model's accuracy and performance metrics, and took a look at the feature importance and the plots produced by SHAP and Lime. So more on the pre-processing and feature engineering. Our design decisions included dropping the final weight feature since it was irrelevant to our model predictions. We dropped the education column and replaced it with an ordinal education numerical column. We replaced missing values with the NaN. We passed categorical data to a one-hot encoder, and then we fit only on training data applied identically to test set. And then here are our features. We have numerical features such as the age, capital gain, loss, and then we have other categorical features such as work class, occupation, marital status, native country. And then here are some of our hyperparameters. So N estimators is how many decision trees the model will build. More trees typically mean higher accuracy but slower training. Max depth limits how deep each tree is. Each tree can ask 6 questions before deciding. If it is too deep, it results in overfitting, and too shallow means it could miss some patterns. Our learning rate was at 0.05, which means the model learns more slowly but more carefully, and there's less risk of overfitting. random state is at 42, just to make the this model reproducible. Overall, our accuracy was at an 87%, which is solid for this data set. Our model was a lot better at predicting those that made under 50K. You see through the precision and recall, less than or equal to 55K or 50K, you see that the values are a lot higher. This is our explainability. We use SHAP and line. These are some of the graphs that SHAP produces. Summary plot, a bar plot, waterfall plot, forest plot, scatter plot. And then line was used specifically for our local explanations. It produces a ranked list of features and assigned weights for one prediction. If the weights are green, then it means it is positive, pushing the prediction towards over 50K. If it's red, it's pushing under 50K. SHAP provides what we call global explanations, meaning it looks at the model as a whole and shows which features are most important overall. It also provides local explanations, meaning it focuses on individual predictions and why the model made the prediction for that single data point, similarly to LIME. But LIME is only used for local explanations as it does not provide global explanations. Then here are some of our limitations and challenges. For the user input, our model is trained on a preprocessed CSV dataset with specific features, which means each user input will have to have the same features in the same CSV format. In our dataset, there is a large class imbalance. There's about 75% of the dataset is below 50K. This causes the SHAP base value to be very low, meaning that before the model predicts, it is already thinking that a person is making below 50K. This also makes the model predict those that are under 50K more correctly. And the last one is our one-hot encoding, which split the columns into multiple sub-columns. This gives the model more feature space, which can make it harder for non-technical people to read. This grew our input feature size from 14 to 84. And then this is our project development timeline. We went with an agile/waterfall hybrid, meaning that the bulk of the beginning of our project, we spent it researching and planning the entirety, and then we went through multiple sprints to actually developing the system. Our researching and planning included what was a black box model, how to interpret it, choosing our data set, and choosing which algorithm to use for our model. And then we went ahead with our data preparation. We cleaned the data set and handled any missing values it had. And then we worked on the model development, implementing the XGBoost algorithm, and training and validating its results. And then we went with the explainability features. We included SHAP mainly for its global insights, as well as it also includes local explanations. And then we use LIME specifically for local explanations and also to kind of cross-validate between SHAP. Finally, we implemented the Streamlit UI. It's our user interface, which allows users to upload their own data values, predict, and see which features are most important to their data. In conclusion, our XGBoost model trained decently with an 87% accuracy, considered to be a standard competitive result. SHAP and LIME was used for explanations. SHAP provided global and and local explanations. And Lime was used specifically for our local explanations. They both provided graphs and plots to show which features were the most important to each prediction. And then our user interface was built with Streamlit. It allows for direct user input or a entire CSV file upload. And then after the model makes its predictions, it will provide the SHAP and Lime explanations. My name is Dane Tran, and this is SP-103-BlackBox, and this is our final demo. So welcome to the income prediction dashboard. This interactive tool predicts whether an individual is likely to earn more or less than 50K a year. There are two options that you have. You can either input the data manually or upload a whole CSV file. And then these are just some of the requirements and clarifications we have. You're uploading a CSV file, it has to contain these columns or features. And then this is just a mapping of the education levels. And alongside prediction, our system also provides SHAP and Lime explanations. And this is where we can input the data. So like as I previously stated, you have two choices. You can either directly input each value or you can upload a whole CSV file. And I'll show you both options. First, I'll do the direct input. So I'll just put my own information in. 21, Asian, working class, say private. I'm a male, years of education. You can look up and see where you're at. I'm going to say 12. Capital gain, 0. Capital loss, 0. Never married. Occupation, line cook. Hours per week, about 30 hours. I am not in a family in the United States. And then from there, you hit submit data. And then it will create a data frame based on the information you provided it. And then you can view it right here. So the age, working class, private, all the information you just input. And then after that, you can click predict salary. The model will do its work, and then the information is provided here. You can see that there is a 99.4% chance that I make less than 50K. And it's pretty true. And then after that, below are the SHAP and Lime explanations. There are a couple different graphs for SHAP. You have the summary plot, and below each graph, it provides an explanation of what it shows. So this is the summary plot. Here is the waterfall plot and the force plot. And then I'll go to Lime, and then this is the graph for Lime and the individual weights of each feature. Also the explanation. And now I will show myself inputting a whole CSV file. Just click upload here, and then I have this file with 3 entries in it. You can view the information here, and then similarly like before, click predict salary, and then for each entry here is the prediction and then the probabilities for each class. And then like before, you can see all the different graphs. It's a summary plot, waterfall plot, and the force plot. So an additional feature between the individual inputs and a CSV file upload is that you can see each instance of explanations for each entry. So for example, this is the first entry in our CSV file, and if we just go up, we can see the next entry, and you see that the waterfall plot changes. You go up one more time, you'll see the last entry in our file. And then similarly, you can do the same for the force plot. And the line explanations are also include that feature. And then like before, here are the features and their specific weights for each prediction.